Welcome to Lesson 13 of Applied Physics. This lesson covers rotational motion, including looking at planetary motion, motions of wheels, gyroscopic motion, and, of course, spinning wind turbines. In this lesson, you will cover the following objectives: kinematic equations of rotation, Newton's universal law of gravity, and Kepler's three laws of planetary motion. Just like when we examined linear motion, rotational motion has analogous quantities. Throughout this lesson, you should be aware of the similarities of these concepts to the corresponding ones from the previous linear motion discussion. The figure at the top can be imagined to slide over the reference frame in A. This is a polar coordinate frame which has many similarities to the Cartesian coordinate system we explored during the mathematics lesson. As you can see from the figure, you realize that the angle is the ratio of the arch length to the radius of the circular motion. For example, if you are sweeping through a 30-degree angle and you double the radius of your circle, you will have to double the arch length to obtain the 30 degrees. We tend to measure radius and arch length in the same units, usually meters, and hence the ratio of meters to meters gives us a unit for theta of the radian, not degrees. Based upon this idea, we know that a complete circular rotation is 360 degrees, or a value of 2 pi. This will be the useful one that we talked about for the conversions. You must convert all your rotational motion problems into radians. We briefly talked about rotational measurement systems and polar coordinates during the mathematics review session. Here is a brief review of that material. Remember when you work problems in polar coordinates that you must convert your measurements to radians rather than degrees. Here are some review details about radian measure. The angular displacement is defined as the angle the object rotates through during some time interval. Every point on the disk undergoes the same angular displacement in any given time interval. Notice that the arm is rotating about an axis of rotation known as the elbow. Can you see the similarities to the unit circle provided in the other diagram? Recall the average linear speed, v, was the rate of change of linear distance. A ratio of the linear distance from A to B in the time interval t as well. Here we are looking at angular speed, or omega, as the angular displacement to time interval ratio. The figure shows an object that is rotating in the positive or counterclockwise direction. Notice the angular speed is noted by the Greek letter W, set omega, and the linear speed was noted as v. In this rotational motion, the linear speed has a constant magnitude but a constantly changing direction. Note in this rotation that the angular speed is like the corkscrewing rate, and if that corkscrewing value noted in the figure as rotating counterclockwise about the y-axis grows or shrinks, then you have this term known as angular acceleration, which is noted by the symbol Greek letter A or alpha. So a practical example of this would be when a wind turbine was stopped for maintenance and then the brake was released. As the turbine begins to spin, it is increasing its angular velocity. The fact that the angular velocity is changing gives rise to the term known as angular acceleration. The spin or rotational velocity is either parallel or anti-parallel to the acceleration depending upon whether the object is speeding up or slowing down and changing direction of rotation. In the figure to the left, you see that point A and B will have different linear velocity values, but the turning table will have the same angular velocity, rotations per time, no matter which point, radial distance, you choose from the center. So linear velocity is dependent upon the radius while the angular velocity is constant. In the second figure, you see that the angular velocity can be a constant amount whether or not the axis of rotation is pointed up or down, or left or right. The angular velocity is the corkscrewing type motion that describes the rate at which an object is spinning on an axis. If these vectors grow or shrink, then we have an angular acceleration. We can also have an angular acceleration if the rotating object changes direction, such as going from having the axis pointed up like in A to right like in B or down like in C. This would be a directional change and not a magnitude change, but nonetheless it is still a change in angular velocity and hence an angular acceleration. Always draw pictures of the problem and determine the size and direction of any changing motions. Try and use linear to angular analogies when thinking about the terms as they have been defined. The equations on the right side of the table should be very familiar to you after your initial study of linear kinematics. They are the kinematic equations associated with objects with a constant linear acceleration. The equations on the left side are those rotational kinematic big three equations where the rotation of the object about a fixed axis shows a constant rotational or angular acceleration. It's all about the radius. What does that mean? Well, if you want to go from an angular component of motion to a linear motion component, you just need to multiply by the radius. Centripetal acceleration occurs because of a force pulling an object toward the center of the circle it is rotating in. This force is called a centripetal force and will be discussed in up-and-coming pages. For now, learning the definition of the centripetal acceleration is the key. How do we get this center-seeking direction to follow the pictures and terms as we determine the effect of a constant speed, but a constantly changing direction? It's all about sliding the vectors and doing a vector subtraction or difference. Notice how the change in velocity vector points toward the center of the circular motion. From the equation on the right, you can see how centripetal acceleration, which is velocity squared, has been replaced with the rotational equivalent, omega times radius, which could now be used to find the centripetal acceleration. The total acceleration is a combination of the centripetal, caused by changing direction and a centripetal force, and any tangential or linear acceleration caused by a change in speed or an unbalanced force in the direction of the linear motion. So together, the total acceleration is a combination of the two perpendicular components of centripetal and tangential acceleration. When dealing with the vector nature of angular quantities, assign a positive or negative direction in the problem. A more complete way is by using the right-hand rule. Grasp the axis of rotation with your right hand, wrap your fingers in the direction of rotation, your thumb points in the direction of omega. In this image, the car is traveling about a circular path with a constant speed. How can it be accelerating? It is accelerating because it is constantly changing its directions. Remember that acceleration is both a magnitude and a directional vector quantity. During our study of linear kinematics, all we were worried about was a change in speed. Now we are worried about a change in direction or a change in speed, either or, both or none. If there is some kind of change in velocity, there will be an acceleration. Do you remember what causes an acceleration? An unbalanced force. In this case, a center-seeking force called centripetal force. Here are two examples where force diagrams have been drawn. Notice the centripetal force component is pointing toward the center of the circular motion that is being performed. To help solve this problem, draw a free body diagram showing and labeling all the forces acting on the object. Choose a coordinate system that has one axis perpendicular to the circular path and the other axis tangent to the circular path. Find the net force toward the center of the circular path. This is the force that causes the centripetal acceleration. Solve as in Newton's second law problems. The directions will be radial and tangential. The acceleration will be the centripetal acceleration. There are many specific situations where forces that cause centripetal acceleration are used. Level curves, banked curves, horizontal circles, and vertical circles. Friction is the force that produces the centripetal acceleration. You can find the frictional force using the coefficient of friction and knowing your speed and turning radius. The necessary force needed to make a car travel around an unbanked curve is supplied by friction in the tires. Each of these examples will also be illustrated in the textbook. Usually the textbook illustration helps derive the formula from the foundational principles. A component of the normal force adds to the frictional force to allow higher speeds. A banked curve uses the friction from the tires as well. However, you get some extra force from the component of the normal force pushing your vehicle back toward the center of the road. Again, your textbook will have the derivation of this useful equation. What about objects that are suspended and move in a horizontal circle like the one shown here? Now, a component of the tension in the wire is supplying the necessary centripetal force. Do you think you can apply this formula to any setting in wind energy technology? What if you were swinging from a point on a blade back toward the tower? Have you ever ridden a roller coaster that did an upside-down power loop? In a vertical circle, look at the forces at the top of the circle. The minimum speed at the top of the circle can be found. An analysis of the Hot Wheels double loop stunt which occurred at the X Games in 2011 can be found doing an internet search. Taking your life into the hands of a physics equation really takes some nerve. So does climbing a wind tower and hanging from a cable and a harness. Don't be tricked by any fictitious forces because you heard the term in common conversation. Oftentimes, common conversation doesn't fit the scientific norm. In the graphic, the symbol R means the direction of the force from m sub 1 to m sub 2. It is a unit vector noting direction only. Since every particle is attracted to every other particle in a room or even at the beach, you are being attracted to your best buddy who is walking beside you, as well as his best girl. It's really all about the mass. Since you have it, he has it, and she has it, you are going to be attracted. It's a universal law. Please remember the bro code. No matter how attractive she is, gravitationally, you should do your best to overcome the force and avoid any extra attraction to her. Another example of an inverse square law is the law that shows how light falls off from a photographer's flash. Notice that the farther away the light source, the less intensity of light that falls on the model. In this YouTube video, you see Peter Griffin demonstrate universal gravitation. According to Brian, Peter is so massive that the attraction of objects about him is an example of orbital motion. Funny use of science ideas on a modern television cartoon. Click on this link if you're interested in another television example of science. How was the gravitational constant determined? Well, it was determined experimentally by Henry Cavendish in 1798 using a mass and mirror setup similar to the one shown. The optical lever, a light source and mirror, spun to give an angle measurement based upon the movement of a small mass near another mass. The twisting or torque caused the mirror to swing through a specific arch length, which was ultimately calibrated to find our current value of the universal gravitational constant G. You can follow along in your textbook and see how the mass of the Earth can be calculated from knowing the planetary information such as the radius of the Earth, the acceleration rate due to gravitational attractions, and the universal gravitational constant. Substitute these values in the equation and you will see an excellent approximation of the mass of the Earth.